Hi, this is Jeff Brunner. I'm a member of the ABB Application Engineering team, and the topic of this video is how to apply an ACH580 with an E-Clipse bypass in a cooling tower application. More specifically, how to set it up to do ice control in a colder climate where ice formation may be an issue. In an E-Clipse bypass system, there are many different ways it can be configured to implement this feature, depending on what the control configuration of a particular application is. And this video is going to cover the more common ones. And just a final remark, this will be a discussion with respect to an application which features both an ACH580 and an E-Clipse bypass. There's a separate tutorial available to review this same topic when only a standalone ACH580 is in the system. The most common way to control ice on a cooling tower with an ACH580 E-Clipse bypass system is to run the cooling tower in reverse. What this does is force warm air over the iced surfaces, which melts the ice. The picture to the right is a simplified representation of a cooling tower, and as drawn here, the blue arrows indicate the direction of airflow during normal operation. So cool air is drawn in from the sides and passes over the hot water, extracting heat in the process. The warm air is then exhausted out the top, and it's these inlet louvers on the intake side that can become iced over in cold weather if it's not managed properly. When the fan runs in reverse, the direction of airflow is in the opposite direction, and this is represented by the red arrows in this drawing. This forces the warm air out over the iced surfaces, therefore melting the ice. And as I alluded to earlier, the execution of the reverse operation depends on the way the controls of a particular application are implemented. In this presentation, I'm going to go over the more common ones, which I'll itemize here, and then separate slides will be prepared to go into detail about how the ACH580 and E-Clipse bypass would be configured for each. The first and most common configuration is traditional hardwire control. This is also the default configuration with an ACH580 E-Clipse bypass system. In this case, the frequency reference is wired to an analog input on the ACH580, and the control inputs, the start-stop, the safeties, other interlocks, they're all landed at the discrete inputs of the E-Clipse bypass. The next configuration that's quite common is where control is done over comms. In this presentation, I'll cover two examples because the way it is done may be a bit different depending on what protocol is implemented in the application. And so here I'm going to discuss one implementation using Modbus and another implementation using BACnet. And finally, another less common control strategy is hardware for primary control, but serial comms to initiate the de-ice request. And this could be by design, or it might also be a case where the de-ice functionality was initially overlooked and the control wiring to initiate it has not been pulled to the system. And so in this case, where there is also comms in the application, there is a workaround where the de-ice request can be initiated over comms. Before launching into de-ice control for an E-Clipse bypass system, I'd like to take a moment to briefly introduce some of the high-level system considerations to be aware of, which may help support your understanding of the content to follow. First, understand that the E-Clipse controller is the primary controller in the system. The EFB connection on the ACH580 is configured for Modbus and used to exchange control and status with the E-Clipse controller. Therefore, all the primary control inputs, start, stop, start interlocks, run enables, etc., they're all landed at the E-Clipse control board, and this information is then passed to the ACH580 over Modbus. Exceptions to this are frequency reference inputs, which are landed at the ACH580. So analog input references, constant frequencies, PID-related references, they're all managed at the ACH580, anything reference related. However, references set over serial comms are passed through the E-Clipse controller to the ACH580 because all communications with a building automation system are handled at the Eclipse. And finally, the most important takeaway of this introduction is to point out that reverse operation for de-ice control is not possible in bypass mode. This is only possible when the ACH580 is controlling the motor. And with that, let's get into the rest of the material. With hardwire control, all the wiring is going to be landed at the ACH580 or E-Clipse input terminals. The normal start request is going to come in on digital input 1 of the E-Clipse control board. Along with this, the normal frequency reference will be landed at the analog input 1 terminals of the ACH580 control board. For de-ice operation, there's a separate start reverse request available with the E-Clipse bypass, and this will be landed at digital input 2 of the bypass. Understand that this is an independent start request from normal mode and will start the drive without requiring the normal start input to be closed. And as well, it will command reverse operation. For the de-ice frequency reference, we're going to use the same input wired to digital input 3 of the ACH580, which will be configured for the constant speed required for the de-ice operation. And then finally, for the reverse operation, we need to make sure that the ACH580 is set up to allow reverse. And to the right is a wiring diagram that summarizes what this wiring would look like, which has terminal designations for both the ACH580 and the E-Clipse control boards. And then to the left is a summary of the parameters required to set this up for both the ACH580 and the E-Clipse. So for normal start mode operation, this is going to be set up at E-Clipse parameter 1601. And this will be configured for DI1, and this is the default setting. And then for the frequency reference, this is going to be set up on the ACH580 in parameter 2811, and this will be analog input 1, and this is also the default setting. Switching to the de-ice operation, we are going to configure the de-ice start request at E-Clipse parameter 1630, and this is going to set up DI2 to be a start reverse input. And then for the de-ice frequency reference, we're going to use the constant speed up in the ACH580. And so we will use the DI3 as the trigger for the constant frequency. And this is set up at ACH580 parameter 2822. And then we'll also need to set up what the actual frequency reference will be in the de-ice mode. And we'll set this to minus 30 hertz. And then finally, as I said, we need to enable reverse operation. And this is set up in ACH580 parameter 20.21, where we set this to request. Okay, so here I brought up the ACH580 keypad so we can have a look at how this behaves in operation. I've got an ACH580 bypass demo case configured as described here. And on it, there are analog and digital inputs that can be activated to verify the system configuration. In the upper right-hand corner, you can see the normal mode operating frequency reference, and this is controlled by an analog input on the demo case, which you can see move around as I adjust this potentiometer. So let's just leave it set at something that's other than our DI set point. So when I activate DI1 on the E-Clipse bypass, you'll see the drive's output frequency begin to ramp up to the normal set point. And then after I activate DI2 on the E-Clipse bypass, which is also wired to DI3 on the ACH580, you'll see that set point switch to the DI set point, which you can see in the upper right-hand corner. And then the output will ramp down through 0 and then ramp to the DI set point. And then after the DI interval is satisfied, DI2 on the E-Clipse bypass is opened and the normal mode set point is restored. And then we'll ramp back through 0 and then up to that normal operating set point. And then finally DI1 is open and the drive stops. And I guess the last point I want to make is that when you activate, if you're not running currently and you simply activate DI2, you can initiate a start in de-ice mode without having to already be running. And so here from a stop state, I've just activated DI2, and now we are simply starting in de-ice mode. And then I'll open DI2 and the drive will just stop. This next slide presents an alternative approach to hardwire control with simplified wiring. From a setup standpoint, everything is the same as the typical hardwire approach from the previous slide, except for the constant frequency trigger. So the extra wiring to use DI3 on the ACH580 control board is removed, and a control bit in the interface between the E-Clipse and ACH580 is used instead. And so on the right, you can see that this extra wiring has been removed. To the left, I've highlighted the change in setup for de-ice frequency select to be bit 2 of ACH580 parameter 58.18, and this is the reverse request bit. And this parameter is actually the control word that's exchanged between the E-Clipse and the ACH580. For reference, I've pulled up a few of these control bits in that control word that I was referring to that gets exchanged between the bypass and the ACH580. And specifically, we see here the bit 2 is this reverse request bit. And next, I'll bring up the ACH580 panel, and we can take a look and see how some of these bits interact with the E-Clipse bypass. I've brought up the ACH580 keypad here, and let's begin by going in and taking a look at that control word that I referenced previously, and we can just observe what the interaction is with the E-Clipse bypass when we start toggling the control inputs. So we'll navigate to the full parameter list, and we're looking for group 58, and we need 5818. So we'll scroll down to 5818, and here we see the EFB control word. We can open this up, and we can see first, referring back to the bit definitions that I was telling you about, that the least significant bit is asserted, and this is the stop command. So I'll begin by throwing DI1 on the E-Clipse bypass, which is the run normal command. And here we can see now that bit 0, the least significant bit, is cleared, and bit 1 is set, and this is the start command. And so I opened that input, and now we can see the stop is asserted. Now I'm going to close DI2, which is the reverse request. And now this 6 is bits 1 and 2, so this is a start request as well as a reverse request. And so this is that bit 2 that we're going to pick up and set up now as our trigger for the constant frequency. So I'll close that, and we'll navigate back out of here and go into the setup for the constant frequency select, which I haven't changed from the last slide. So that's in group 28, 22, and we see that it's still DI3. So we'll go in here, and some previous presentations I've highlighted this usage of this other option, which is now I can go pick any bit that I want in any of the parameters. So now I can scroll down to group 58 and select 5818, and then go to 5818, and I will select bit 2 and save. And so now we can see the constant frequency select has been set to 5818 bit 2. So now I can back all the way out, and we can just confirm the operation. So I'll first close DI1, and now we're running in normal mode. We'll ramp up to the set point. Then if I close DI2, now I've picked up that reverse request bit, and that has become my trigger. And I'm at my DI set point now, and we're ramping through 0, then to the DI set point, and then I can open DI2, and we'll return to normal operation. I can open DI1, and we'll stop. And then, as I said in the previous slide, with this DI2 reverse request start request, I should say, on the bypass, I can initiate just a de-ice request without first starting in normal mode. So I'll just close DI2, and now I've directly issued a request for de-ice mode. With serial communications control, all the control inputs are going to come in over the embedded field bus channel, and we're going to begin with an example using the Modbus protocol. And I'd like to state at the beginning of this slide that this is not going to be an in-depth tutorial on Modbus. We have separate technical content available that covers the Modbus protocol and how it's applied to our drive products in detail. As well, I'd also like to state that there's a companion tutorial to this one for the standalone ACH580 and de-ice control, and content in that presentation includes a demonstration using protocol-specific client applications which control the same communication objects that will be referenced here. Therefore, these slides on communications in this presentation will focus primarily on the differences in setup only, and I'll reference you back to the de-ice presentation on the standalone ACH580 if you want to see what the interface looks like with those clients. And so to the right here, we see the control board IL summary for both the E-Clipse bypass and the ACH580, and you'll see that there are no control connections. The only wiring required in this case is the RS-485 wiring, which must be landed at the EFB port on the E-Clipse. And so from a setup standpoint, the protocol itself is selected at E-Clipse parameter 9802, and this should be set to Modbus. The start command source is set up on the bypass at E-Clipse parameter 1601, and this should be set to COM. And Over Modbus, the start-stop command will be controlled in Modbus holding register 40,001. The frequency reference location is set up in the ACH580 at parameter 2811, and this should be set to EFB ref 1, and the reference will be set at Modbus holding register 40,002. Now the source for the de-ice frequency select will also be set up on the ACH580, and this will be at parameter 2822. And here we're going to use the other option, which lets us select any other bit that we want, and we're going to use this user bit 0, which is in the main control word, and this is accessible at parameter 601. And this is also controlled in Modbus holding register 40,001. And then the de-ice frequency itself is set in the ACH580 at parameter 2826, and we'll leave that as we have at minus 30 hertz. And then finally, we still need to have that set up to allow reverse operation at 20.21, and that's set to request. And so again, I'll refer you back to the other presentation for a more detailed presentation of the Modbus client running. Now we'll switch to an example using BACnet. And I'd also like to state at the beginning of this slide that this is not going to be a detailed introduction to BACnet. We have additional technical content which covers that topic in much more detail. Now, most of the setup here is going to be the same as it was with Modbus, with the obvious exception of the protocol selected, which will be BACnet for this example. But the wiring and the other remaining setup will be the same. And so, as I said, 9802, we'll set that to BACnet. Start command still coming in over comms. But with BACnet, this is going to be controlled by binary value 10 frequency reference, again, over EFB. This will be controlled by BACnet object analog value 16. The de-ice select, again, setup is the same, but here with BACnet, it's controlled by BACnet object binary value 34. And then the de-ice setup and the reverse request is also all the same. And as with Modbus, if you're interested in seeing an actual example of this control using a BACnet client, please see the de-ice presentation for the standalone ACH580. Our next example is with an application that requires mixed control sources. So the primary control will be done directly at the control terminals of the 580 or E-Clipse control boards, while the de-ice control will be managed over Modbus. From a configuration standpoint, the protocol is going to be set to Modbus. However, the start command is reconfigured to be DI1 at the E-Clipse control board, while the frequency reference is reconfigured to be at analog input 1 of the ACH580 control board. The de-ice trigger is still set to be user bit 0, which again is controlled by Modbus holding register 40,001. However, this trigger bit will be picked up at a different ACH580 parameter, in this case, 5818 bit 12. And here I'm going to refer you back to the version of this topic for the standalone ACH580, where there's a detailed discussion of why this bit location is moved from parameter 601 to parameter 5818. And then the remaining de-ice setup is the same, with the same negative 30 hertz de-ice set point, and we've got our reverse operation enabled. And to the right, we can see that the primary control wiring is landed at the control terminals of either the ACH580 or E-Clipse bypass, and of course the 45 wiring for serial communication is required for the de-ice control. And as with the previous two slides, there's a complete demonstration of this control strategy with a Modbus client and demo case in that previous version of the topic for the standalone ACH580. So that concludes our discussion of de-ice control on a cooling tower with both an ACH580 and an E-Clipse bypass in the system. We covered 4 different control options. The first was hardwire control only, and we covered both a typical wiring option and one with simplified wiring. Then we reviewed 2 different communication options, one with Modbus and one with BACnet. And finally, a mix of control strategies with hardware for primary control and serial comms for de-ice. And then a few additional remarks about other options beyond use of a constant frequency. First, if using comms, a negative frequency reference can be sent to the primary set point. That's one option. You can also command reverse operation at the primary set point if a different de-ice set point isn't required in the application. And lastly, regarding Modbus specifically, we covered an example using the ABB drives profile. Just know that it's possible to achieve the same functionality using the DCU profile. And then finally, as always, reach out to your local ABB representatives if you have any questions. Thanks for watching.